Oh my god. We haven't been live since what? Last week? Holy shit, it's been a long time. I missed this, honestly. Yeah, so welcome back to another live. Um Updates, let me think. Last week we had exams and we had two exams. It was math and organic chemistry one. And I haven't gotten my result yet for organic chemistry one, but I've gotten my result for math. And let me tell you, we passed. We passed that shit. Holy, oh my god! I'm so glad that's over. Oh my god, I'm really bad at math. I'm so bad at math, but I'm just glad that it's um over. So yeah, that, I'm so happy. And yeah, so now I'm just waiting for my organic chemistry test or like results. So yeah, it's gonna be good. And now I started a new course called medical chemistry or like introduction to medical chemistry and bioorganic chemistry, which is pretty interesting. So it's like about peptides and yeah, like carbohydrates and all that. And with medical chemistry, it's like how it works in the body. So we're gonna read some and have a good time, honestly. Yeah, so also I just finished recording my first video. Like, the plan for this channel is to teach other about chemistry, like those who are having a hard time, or like those who are interested in chemistry. And hopefully it goes well. I don't know, it's my first video. But yeah, everything can happen. So yeah, currently pretty cold. It feels like it's Siberia. Like the Siberia wind is coming and it's pretty cold. So not even my jacket can help. But yeah, hopefully you guys are having a great time and hopefully your guys' exams are going well or did go well, hopefully. And yeah, so let's just get started, I guess. There we go. What is a drug? Basically. All right. So yeah, gonna read some. Hopefully, YouTube doesn't take it down. But yeah. So, what is the drug? Medical chemistry involves the design and synthesis of pharmaceutical agent that has a desired biological effect on the human body or some other living system. Such a compound could also be called a drug. But this is a word that many scientists dislike because of the way it's viewed by society. With media headlines such as drugs menace or drug addiction sweeps city streets, this is hardly surprising. However, it suggests that a distinction can be drawn between drugs that are used in medicine and drugs that are abused. But is this really true? Can we draw a neat line between good drugs like penicillin and bad drugs like heroin? If so, how do we start to define what is meant by a good or bad drug? Where will be excuse me, need to not be dry. Where will we be where will we place a so-called social drug like cannabis in this divide? What about nicotine or alcohol? Our answers depend on who we ask. As far as the law is concerned, the dividing line is defined in black and white. As far as the party-going teenager is concerned, the law is an ass. Wait, what? Whoa! That language in my book? Hold up. Alright, that law is an ass. As far as we are concerned, the questions are irrelevant. Trying to divide drugs into two categories, safe or unsafe, good or bad, is futile or could even be dangerous. First, let us consider the good drugs used in medicine. How good are they? If a drug is truly good, it will have to do what it meant to do, have no toxic or unwanted side effects, and be cheap and easy to take. How many drugs fit these criteria? The short answer is none. There is no pharmaceutical compound on the market today that can completely satisfy all these conditions. Admittedly, some comes quite close as the ideal of penicillin. For example, has been one of the safest and most effective antibacterial agents ever discovered. Yet, it too has drawbacks. It cannot treat all known bacterial infections, and as the years have gone by, more and more bacterial strains have become resistant. Moreover, some individual oh my god individuals can experience severe allergic reactions to the compound. Penicillin is relatively a safe drug, but there are some drugs that are distinctly dangerous. Morphine is one such example. It is an excellent analgesic. What? Analgesic. Anal, analgesic, yet it causes serious side effects, such as tolerance, respiratory depression, and addiction. It can even kill if taken in excess. Barbiturates are also known as to be dangerous. At Pearl Harbor, American casualties were given barbiturates as a general anesthetics. Before surgery, however, a poor understanding of how Barbie barbiturates are stored in the body led to many patients receiving a fatal overdose. In fact, it is thought that more casualties died at the hands of the anesthetics at Pearl Harbor than died of their wounds. To conclude, the good drugs are not as perfect as one might think. What about the bad drugs then? Is there anything good that can be said about them? Surely, there is nothing we can say in defense of highly addictive drug heroin. Let's look at the facts about heroin. It is one of the best painkillers known to medicine. In fact, it is named heroin at the end of the 19th century because it was thought to be the heroic drug that will banish pain for good. Heroin went on the market in 1898, but had to be withdrawn from general distribution 5 years later, when its addictive properties became evident. However, heroin is still used in medicine today, under strict control, of course. The drug is called diamorphine. Diamorphine. It is a drug of choice for treating patients dying of cancer. Not only does diamorphine reduce pain to acceptable levels, but it also produces an euphoric effect that helps to counter the depression faced by patients close to death. Can we really condemn such a drug as being all bad? By now, it should be evident that the division between good and bad drugs is a woolly one and is not really relevant to our discussion of medical chemistry. Alright. All drugs have their own and bad points. Some have more good points than bad, and vice versa. But like people, they all have their own individual characteristics. So how do we define a drug in general? One definition could be to classify drugs as compounds that interact with biological system to produce a biological response. This definition covers all the drugs we have discussed so far, but it goes further. We take chemicals every day and they have a biological effect on us. What are these everyday drugs? One is contained in a cup. Oh, one is contained in the cups of tea, coffee, and cocoa, cocoa, right? Cocoa that we consume. All of these beverages contain the stimulant caffeine. Whenever you take a cup of coffee, your drug use. Okay, so I can't even drink coffee anymore. Apparently, whenever you take a cup of coffee, you're a drug user. We can go further. Whenever you crave a cup of coffee, you're a drug addict. Even children are not immune. They get their caffeine shot from Coke or Pepsi. Whether you like it or not, caffeine is a drug. When you take it, you experience a change of mood or feeling. So too, if you're a worshipper of the nicotine stick, the biological effect is different. In this case, you crave sedation or calming influence, and it is the nicotine in the cigarette smoke which induce the effect. Alcohol is other example of a social drug, and as such causes society I can't even speak society more problems than all other drugs put together. One only has to study road accident statistics to appreciate the fact if alcohol was discovered today, it will probably be restricted in exactly the same way as cocaine, considered in a purely scientific way. Alcohol is the most unsatisfactory drug, as many will testify. It is notoriously difficult to judge the correct dose required to gain the beneficial effect of happiness without drifting into the higher dose level that produce unwanted side effects, such as staggering down the street. Alcohol is also unpredictable in its biological effects. Either happiness or depression may result, depending on the user's state of mind. On on a more serious note, addiction and tolerance in certain individuals has have ruined the lives of addicts, addicts and relatives alike. How much is this? Holy shit! All right, it's a lot to read. Uh, Our definition of a drug can also be used to include less obvious compounds, for example, poisonous and toxins. These are also interact with biological system and produce a biological response. A bit extreme perhaps, but a response all the same. The idea of poisons acting as drugs may not appear so strange if we consider penicillin. We have no problem in the effects on human cells. Even drugs that do not act as poisons have a potential to become poisons, usually if they're taken in excess. We have already seen this with morphine. At low doses, it is a painkiller. At high doses, it is a poison that kills by suppressing breathing. Therefore, it is important that we treat all medicines as potential poisons and treat them with respect. Interesting. There is a term used in medical chemistry known as the therapeutic index, which indicates how safe a particular drug is. The therapeutic therapeutic index is a measure of a drug beneficial effects at a low dose versus its harmful effects at a high dose. To be more precise, the screw that word, honestly. Uh, ther- therapeutic Index compares the dose level required to produce toxic effect in 50% of patients to the dose level required to produce the maximum therapeutic effects of 50% of patients. A high therapeutic index means that is a large safety margin between beneficial and toxic doses. The values for cannabis and alcohol are 1000 and 10, respectively, which might imply that cannabis is safer and more predictable than alcohol. Indeed, a cannabis preparation, nabiximols, has now been approved to relieve the symptoms of multiple sclerosis. All right. However, this does not solely make cannabis safe. For example, the favorable therapeutic index of cannabis does not indicate its potential toxicity if it's taken over a long period of time, chronic use. For example, the various side effects of cannabis include panic attacks, paranoid delusions, and hallucinations. Clearly, clearly, the safety of drugs is a complex matter, and is not helped by media sensationalism. If useful, drugs can be poisoned at high doses or over long periods of use. Does that opposite hold true? Can a poison be a medicine at low doses? In certain cases, this is found to be so. Okay, interesting. Arsenic is well known as a poison, but arsenic-derived compounds are used as a antiprotozoal, and anti-cancer agents. Curare is a deadly poison used by the indigenous people of South America to tip their arrows, such that a minor arrow wound is fatal to their prey. Yet compounds based on the tuberculin structure, the active principle of curare are used in a surgical operation to relax muscles. Under proper control and in the correct dosage, a lethal poison may well have an important medical role. Alternatively, lethal poisons can be a starting point for the development of useful drugs. For example, ACE inhibitors are important as ACE inhibitors are important cardiovascular drugs that were developed in part from the structure of a snake venom. Since our definition covers any chemical that interacts with any biological system, we can include all the pesticides used in agriculture as drugs. They interact with a biological system of harmful bacteria, fungi, insects to produce a toxic effect that protects the plants. Even food can act like a drug. Junk foods and fizzy drinks have been blamed for causing hyperactivity in children. It is believed that junk foods have high concentration of certain amino acids that can be converted into body to neurotransmitters, chemicals that pass messages between nerves. In excess, these chemical messages overstimulate the nervous system, leading to a disruptive behavior. Observed in a suspicious sus 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 suspicious. Oh my god. Okay, suspicious individuals. Allergies due to food addictive and preservatives are also well recorded. Some food even contain toxic chemicals. Broccoli? No way. Broccoli, cabbage, and cauliflower, high levels of a chemical that can cause reproductive abnormalities in rats. I'm sorry, what? Peanut and maize, sometimes contain fungal toxins. Fungal toxins in food were responsible for one of the biblical, no, biblical plagues. Interesting. So broccoli is basically Basil contains over 50 compounds that are potentially what carcinogenic, car- carcinogenic, and other herbs contain some of the most potent carcinogens known. Carcinogenic compounds also have also been identified in radishes, brown mustard, apricots, cherries, and plums. Such unpalatable facts might put you off your dinner. Yeah, I'm not gonna eat it. No. But take comfort, these chemicals are present in such small quantities that the risk is insignificant. Therein lies a great truth that was recognized as long ago as the 15th century, when it was stated that everything is a poison, nothing is a poison. It is the dose that makes the poison. Almost anything can taken in an excess will be toxic. You can make yourself seriously ill by taking 100 aspirin tablets, a bottle of whiskey, or 9 kilos of spinach. The choice is yours. What is this, a salt trap? Oh shit. Actually started my math program. Oh no, it's gonna lag so bad now. Shit. Please don't open. Please. Shit. Close. Oh my god. Currently, can you see that? What's going on? No, we can't even see it. Okay. It's because my math program is starting and I'm just gonna close it down. Hurry, hurry. I was just on a nice flow, man. There we go. To conclude, drugs can be viewed as actual or potential poisons. An important principle is that of selective toxicity. Many drugs are effective because they are toxic to problem cells, but not normal cells. For example, antibacterial, antifungal, and antiprotozoal drugs are useful in medicine when they show a selective toxicity to microbial cells rather than mammalian cells. Clinically, silicin okay, clinically Clinically effective anti-cancer agents show a selective toxicity for cancer cells over normal cells. Similarly, effective antiviral agents are toxic to viruses rather than normal cells. Having discussed what drugs are, we are now considering why, where, and how they react. Okay, so key points. Drugs are compounds that interact with biological system to produce a biological response. That's basically a drug. Okay. No drug is totally safe. Drugs vary in the side effects they might have. The dose level of a compound determines whether it will act as a medicine or a poison. Okay, that kind of makes sense. The therapeutic index is a measure of a drug's beneficial effect at a low dose versus its harmful effects at a higher dose. A high therapeutic index indicates a large safety margin between beneficial and toxic doses. The principle of selective toxicity means that useful drugs show toxicity against foreign or abnormal cells, but not against normal host cells. Alright. This is so interesting to me. Maybe I chose the right major, honestly. Who knows? Maybe. Just hope I'm gonna pass organic chemistry. Okay. Drug targets. Why should chemicals, some of which have remarkably simple structures, have such an important effect on such complicated and large structures as a human being? The answer lies in the way that the human body operates. If we could see inside our bodies to a molecular level, we could see a magnificent array of chemical reactions taking place, keeping the body healthy and functioning. Drugs may be mere chemicals, but they are entering a world of chemical reactions which they interact. Therefore, there should be nothing odd in the fact that they can have an effect. The surprising thing might be that they can have such specific effects. This is more a result of where they act in the body, the drug targets. Cell structure. Since life is made up of cell, then quite clearly drugs must act on cell. Figure 1.1 shows the structure of a typical mammalian cell. All cells in the human body contain a boundary wall called the cell membrane, which encloses the contents of the cell, called cytoplasm. Cytoplasm. The cell membrane, seen under the electron microscope, consists of two identifiable layers, each of which is made up of an ordered row of phosphoglyceride molecules. Figures 1 and 2 and 1 3. The outer layer of the membrane is made up of phosphatidylchlorides, whereas the inner layer is made up of phosphatidylethylamines. Holy shit, what a tongue twister. Phosphatidylserides and phosphorylinostols. Each phosphoglyceride molecule consists of small polar head group and two long hydrophobic water-hating chains. Okay, so we have cell, typical mammalian cell. Okay, then we have this, which is in the cell membrane. Up. Okay. In the cell membrane, one moment. In the cell membrane, the two layers of phospholipids are arranged such that the hydrophobic points towards each other and form a fatty hydrophobic center, while the ionic head groups are placed at the inner and outer surfaces of the cell membrane. This is a stable structure because the ionic hydrophilic head groups interacts with the aqueous media inside and outside the cell, whereas the hydrophobic tails maximize hydrophobic interactions with each other and are kept away from aqueous environments. The overall result of this structure is to construct a fatty barrier between the cell's interior and its surroundings. The membrane is not just made of phospholipids. However, there's a large variety of proteins situated in the cell membrane. Some proteins lie attached to the inner or the outer surface of the membrane, while the others are embedded in the membrane, with part of the structure exposed to one surface or both. The extent to which these proteins are embedded within the cell membrane structure depends on the type of amino acid present. Portions of protein that are embedded in the cell membrane has a large number of hydrophobic amino acid residues, whereas those portions that stick out from the surface have a large number of hydrophilic amino acid residues. Many surface proteins also have short chains of carbohydrates attached to them, and those are classed as glycoproteins. These carbohydrate segments are important to cell-cell regulation. Within the cytoplasm, there are several structures, one of which is the nucleus. This acts as the control center of the cell. The nucleus contains a genetic code, the DNA, which acts as a blueprint for all constructions of all the cell's protein. There are many other structures within a cell, such as the mitochondria, the Golgi apparatus, and the endoplasmic reticulum. What a Latin word. But it is not the purpose of the book to look at the structure and function of these organelles. Suffice it to say the different drugs act as on molecule targets at different locations in the cell. Okay. Drug targets at the molecule level. We shall now move. One moment. We shall now move to the molecule level because it is here that we can truly appreciate how drugs work. The main molecular targets for drugs are proteins, enzymes, receptors, and transport proteins, and nucleic acids, DNA and RNA. These are large molecules, macromolecules, having molecules weights measured in the order of several thousand atomic mass units. They are much bigger than a typical drug, which has a molecular weight in the order of a few hundred atomic mass units. Okay, the interaction of the drug with a micromolecular target involves a process known as binding. There is usually of the macromolecule where this takes place, and this is known as the binding site. Typically, this takes the form of a hollow or a canyon on the surface of the macromolecule, allowing the drug to sink into the body of a larger molecule. Some drugs react with the binding site and become permanently attached via a covalent bond that has a bond strength of 200 to 400 kg per mole. However, most drugs interact through weaker forms of interaction known as the intermolecular bonds. These include electrostatic or ionic bonds, hydrogen bonds, van der Waals interactions, and hydrophobic interactions. It is also possible for these interactions to take place within a molecule, in which case they are called intramolecular bonds. See, for example, protein structure and okay. None of those bonds is as strong as the covalent bonds that make up the skeleton of the molecule, and so they can be formed, then broken again. This means that the equilibrium takes place between the drug being bound and unbound to its target. The binding forces are strong enough to hold the drug for a certain period of time to let it have an effect on the target, but weak enough to allow it to depart once it has done its job. The length of the time the drug remains at its target will depend on the number of intermolecular bonds involved in holding it there. Drugs having a large number of interactions are likely to remain bound longer than those who have only a few. The relative strength of the different intermolecular binding forces is also an important factor. Functional groups present in the drug can be important in forming intermolecular bonds with the target binding site. If they do so, they're called binding groups. However, the carbon skeleton of the drug also plays an important role in binding the drug, so its target through van der Waals interactions. As far as the target binding site is concerned, it too contains functional groups and carbon skeletons, which can form intermolecular bonds with visiting drugs. The specific regions where this takes place are known as binding regions. The study of how drugs interact with targets through binding interactions and produce a pharmacological effect is known as pharmacodynamics. We should now consider the types of intermolecular bonds that are possible. Whoops. Alright, so we have the binding site, and we have a macromolecular target, and then it fits, then it's bound to the target, the drug, and it does the intermolecular bonds, which the binding group connects to. Alright, I think I have an idea. Oh. Intermolecular bonding forces. Bonding forces. There are several types of intermolecular bonding interactions, which differ in the bond strength. The number and types of these interactions depend on the structure of the drug and the functional group that are present. Thus, each drug may use one or more of the following interactions, but not necessarily all of them. Okay, electrostatic or ionic bonds. An ionic or electrostatic bond is the strongest of the intermolecular bonds, 2240 kg per mole, and takes place between groups having opposite charges such as carboxylate ion and ammonium ion. The strength of the interaction is inversely proportional to the distance between the two charged atoms, and is also depend on the nature of the environment being stronger in hydrophobic environments than in polar environments. Usually, the binding sites of macromolecules are more hydrophobic in nature than the surface, and so this enhances the effects of the ionic interaction. The drop-off of in ionic bonding strength is with separation in less than in other intermolecular interactions. So, if an ionic interaction is possible, it is likely to be most important in initial interaction as the drug enters the binding site. Okay. Hydrogen bonds. Conventional hydrogen bonds. A conventional hydrogen bond can vary substantially in strength, but normally occurs between an electron-rich heteroatom, the hydrogen bond acceptor HBA, and the electron deficient hydrogen linked to another heteroatom, the hydrogen bond donor. The electron-rich heteroatom that acts as the HBA is usually oxygen and nitrogen, which provides a lone pair of electrons for the hydrogen bond. As far as the hydrogen bond donor is concerned, the hydrogen atom is electron deficient because it is linked to a more electronegative heteroatom X that polarizes the covalent HX bond. Right? Some functional group can act both as hydrogen bond donors and hydrogen bond acceptors. Example, OH and O2. Okay. When such group is present in the binding site, it is possible that it might bind to one ligand as a hydrogen bond donor and to other as a hydrogen bond acceptor. This characteristic is given the term hydrobond flip-flop. What a funny name. Hydrobond flip-flop. Hydrogen bonds have been viewed as a weak form of electrostatic interaction because the heteroatom of the HBA is slightly negative, then the hydrogen of the HBD is slightly positive. However, there is more to hydrogen bonding than an attraction between partial charges. Unlike other intermolecular interaction, an interaction of orbitals takes place between the two molecules. The orbital containing the lone pair of electrons on heteroatom Y interacts with the atomic orbital normally involved in the covalent bond between X and H. This results in a weak form of sigma bonding and has an important directional consequence that is not evident in electrostatic bonds. The optimum orientation is where the XH bond points directly to the lone pair on Y, such as the angle formed between X, H, and Y is 180 degrees. This is observed in the very strong hydrogen bonds. However, the angle can vary between 130 and 180 degrees for moderately strong hydrogen bonds and can be low as 90 degrees for weak hydrogen bonds. The lone pair orbital of Y also have a directional property, depending on its hybridization. For example, the nitrogen of a pyridine ring is sp2 hybridized, and so the lone pair points directly away from the ring and in the same plane. The best location for a hydrogen bond donor will be in the region of space indicated in the figure. Okay. Uh-huh. Okay, so nitrogen is a hydrogen donor, HPA. No, hydrogen is a hydrogen bonding donor, and nitrogen is a hydrogen bonding acceptor. Okay. The strength of a hydrogen bond can vary widely, but most hydrogen bonds in drug-target interactions are moderate in strength, varying from 16 to 60 kg per mole, which is approximately 10 times less than a covalent bond. The bond distance reflects this, and hydrogen bonds are typically 1.5 to 2.20 compared with, okay, for covalent bond. The strength of the hydrogen bond depend on the strength of the hydrogen bond acceptor and the hydrogen bond donor. A good hydrogen bond acceptor has to be electronegative to have a lone pair of electrons. Nitrogen and oxygen are the most common atoms that involved as hydrogen bond acceptors in biological systems. Nitrogen has one lone pair of electrons and can act as an acceptor for one hydrogen bond. Oxygen has two lone pair of electrons and can act as an acceptor for two hydrogen bonds. All right. Several drugs and macromolecule targets contain a sulfur atom, which is also an electronegative. However, sulfur is a weak hydrogen bond acceptor because its lone pairs are in the first shell of orbitals, which are larger and more diffuse than second shell orbitals. This means that the orbital concerned interact less efficiently with the small 1s orbital of the hydrogen atom. Fluoride, which is present in several drugs, is more electronegative than either oxygen or nitrogen. It also has three lone pairs of electrons, and this might suggest that it will make a good hydrogen bond acceptor. In fact, it is rather a weak hydrogen bond acceptor. It has been suggested that fluorine is so electronegative that it clings on tightly to its lone pairs of electrons, making them less likely to be involved in hydro, hydrogen bond interactions. This is a contrast to a fluoride ion, which is very strong hydrogen bond acceptor. Any feature that affects the electron density of a hydrogen bond acceptor is likely to affect its ability to act as a hydrogen bond acceptor. The greater the electron density of the heteroatom, the greater the strength as the hydrogen bond acceptor. For example, the oxygen of a negatively charged carboxylate ion is a stronger hydrogen bond acceptor than the oxygen of the uncharged carboxylic acid. Phosphate and phosphanate ions can also act as a strong hydrogen bond acceptors. Most hydrogen bond acceptors present in drugs and binding sites are natural functional groups such as ethers, alcohols, phenols, amides, amines, and ketones. These groups will form a moderately strong hydrogen bond. All right. Hydrogen bonds, hydrogen bond acceptor, and hydrogen bond donator. More subtle effects can influence whether an atom is good a hydrogen bond acceptor or not. For example, the nitrogen atom of an aliphatic tertiary amide is a better hydrogen bond acceptor than the nitrogen of an amide or an aniline. In the latter functional groups, the lone pair of the nitrogen can interact with neighboring pi systems to form various resonance structures. As a result, it is less likely to take part in a hydrogen bond. Okay. All right. Similarly, the ability of a carbonyl group to act as a hydrogen bond acceptor varies depending on the functional group involved. It has also been observed that an sp3 hybridized oxygen atom is linked to an sp2 carbon atom rarely reacts as a HBA. This includes the alco alkoxy 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 oxygen of esters and the oxygen atom present in aromatic ethers or furans. Good hydrogen bond donors contain an electron deficient hydrogen linked to oxygen or nitrogen. The more electron deficient the deficient 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 electron deficient the hydrogen, the better it will act as a hydrogen bond donor. For example, a hydrogen attached to a positively charged nitrogen atom acts as a stronger hydrogen bond donor than the hydrogen of a primary or secondary amide. Because the nitrogen is positively charged, it has a greater pull on the electrons surrounding it, making attached hydrogens even more electron deficient. Okay, interesting. Um, oh wow, there's a lot to read. Okay, so after this, after I read all this, I think that's enough. Okay, it has been proposed that the pi system present in alkynes and aromatic rings are a region of high electron density and that can act as a hydrogen bond acceptors. However, the electron density in this system is diffuse, and so the hydrogen bonding interaction is much weaker than those involving oxygen or nitrogen. As a result, aromatic rings and alkynes are only likely to be significant hydrogen bond acceptors if they interact with a strong hydrogen bond donor, such as alkyl aminium ion. Normally, any hydrogen atom attached to a carbon atom can be discounted as a potential HBD. HBD sounds like a virus. However, there are some situations where such a hydrogen atom could act as an HBD if there is a neighboring electron withdrawing group. For example, a hydrogen atom attached to an alpha carbon of a ketone is slightly acidic, as demonstrated by the fact that some ketones can undergo ketoenol tautomerism. I remember that in the organic chemistry. Such a hydrogen atom has a very slight positive charge, and so it could form a weak hydrogen bond with a target binding site. Another example is a CH moiety with two electron withdrawing substituents present, such as a difluoromethyl group. See also, okay. What in the hell is that? In yeah. Okay. No, I'm not gonna. All right. CH pi interaction has been identified as weak form of hydrogen bonding, where a slightly acidic CH hydrogen acting as a HBD interacts with the aromatic pi system, acting as a HBA. CH pi interactions are thought to be relatively common in protein structures, but are rarely discussed when it comes to drug design and drug binding. However, it has been proposed that CH pi interactions are important to the activity of the kinase inhibitor, cipotinib. 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 Sounds Polish. Okay. Van der Waals interactions. Van der Waals interactions are very weak interactions. They are typically 2 to 4 kg per mole in strength. They involve interactions between hydrophobic regions of different molecules, such as aliphatic substituents or the overall carbon skeleton. The electronics dis- distribution in natural nonpolar regions is never totally even or symmetrical, and there are always transitions areas of high and low electron densities leading to temporary dipoles. The dipoles in one molecule can induce dipoles in a neighboring molecule, leading to weak interactions between the two molecules. Thus, an area of high electron density on one molecule can have an attraction for an area of low electron density of another molecule. The strength of these interactions falls off rapidly the further the two molecules are apart, decreasing the seventh power of separation. Um, Therefore, the drug has to be close to target binding site before the interaction becomes important. Van der Waals interactions are also referred as London forces. Although the interactions are individually weak, there may be many such interactions between a drug and its target. So the overall contribution of van der Waals interactions is often crucial to the binding hydrophobic forces. Are also important when the nonpolar regions of molecules interact. All right, so it's a weak yeah, very weak interaction. Okay. Dipole, dipole, ion dipole, and cation pi interactions. Many molecules have a permanent dipole moment resulting from a different electronegativities of the atoms and functional groups present. For example, a ketone has a dipole moment due to a different electronegativity of the carbon and oxygen making up the carbonyl a bond. The binding site also contains functional groups, so it's inevitable that it too will all have various local dipole moments. It is possible for the dipole moments of the drug and the binding site to interact as the drug approaches, aligning the drug such that the dipole moments are parallel in opposite directions. If the position the drug if this positions the drug such that other intermolecular interactions can take place between the drug and the binding site, then the alignment is beneficial to both binding and activity. The then binding and activity may be weakened. An example of such an effect can be found in anti-nuclear drugs. All right. The strength of a dipole-dipole interaction reduces with the cube of the distance between the two dipoles. This means that the dipole-dipole interactions fall away more quickly with this distance than electrostatic interactions, but less quickly than van der Waals interactions. An ion dipole interaction is where a charge or an ionic group in a one molecule interacts with a dipole in a second molecule. This is stronger than a dipole-dipole interaction and falls off less rapidly with separation. Frequency relative to the strength. Okay. Interaction involving included induced dipole moment has been proposed. There is evidence that An aromatic ring can interact with an ionic group such as a quaternary ammonium ion. Such an interaction is feasible if the positive charge of the quaternary ammonium group distorts the pi electron cloud of the aromatic ring to produce a dipole moment, where the face of the aromatic ring is electron rich and the edges are electron deficient. This is also called a cation pi interaction. An important neurotransmitter called acetylcholine forms this type of interaction with its binding site. The anti-cancer agent recuparib and the kinase inhibitors vimurafenib and dabrafenib also form cation pi interaction with their target binding sites. Okay, pi-pi interactions. Pi-pi interactions or pi-pi stacking involve interactions between two aromatic heteroaromatic rings. An aromatic ring has two clouds of pi electron density, one above the ring and one below the ring. As a result, two faces of aromatic ring are electron rich. By contrast, the edges of the ring are electron deficient. However, if there are strong electron withdrawing substitutions, substituents, I can't even substituents present, the polarity is reserved such that the faces become electron deficient and the edges become electron rich. Because of this, the rings can be defined as having a quadruple moment. Yeah, okay. Quadruple moment, therefore, two factors are involved in determining the strength of pi-pi interactions: the interaction between the two quadruple and the van der Waals interactions. Pi-pi interactions can occur between aromatic heteroaromatic rings in the number of rotation, and it is in the order of 10 kg per mole, which is significantly higher than van der Waals interactions. Moreover, compared with van der Waals interactions, the groups can be further apart. The relative rotation of two aromatic rings can vary, but are generally defined as parallel face-to-face or T-shape edge-to-face. The face-to-face interactions can be defined as a sandwich or displaced offset. When the rings are in a sandwich arrangement, van der Waals interactions are predominant, and when the rings are in T-shaped arrangement, the interaction between those two quadruples is predominant. Okay, predominant. The offset parallel arrangement allows both types of interactions to come into play. Okay. The T-shaped arrangement of pi-pi interactions is observed in the binding of ponatinib, and okay, with their respective binding sites. Parallel interactions are seen with the kinase inhibitor pexidartinib and its binding site. Halogen bonds. A halogen bond involves a favorable interaction between a halogen and an electron-rich atom, such as nitrogen or oxygen. The halogen bond is similar to hydrogen bond. The only difference between the halogen is involved rather than hydrogen. Like halogen bonds are relatively strong, 5 to 180 kg per mole, and directional, with the strongest interaction occurring when the angle between three groups involved, ARXI, okay, is 180. In order to act as a halogen bond donor, the halogen needs to be electron deficient, which can occur if it's linked to an electron withdrawing group, such as an aromatic ring. It might seem counter is what counterintuitive to consider a halogen as being electron deficient, but the valence electron, particularly the larger halogens, are polarizable and quite diffuse. The larger the halogen, the stronger the halogen bond. Okay. Although there is a significant number of drugs containing F or fluor or chlorine, the interactions that such drugs make with the targets rarely involve halogen bonding. Halogen bonding is more likely if a bromine or iodine is present. However, the number of drugs that containing Br and I substituents is relatively small. There are a number of reasons for this. For example, iodine and bromine are good leaving groups, and if they're attached to an alkyl group, and if they're attached to an alkyl group, the compound is likely to act as an alkylating agent and have toxic effects. This is not the issue if the halogen is an aromatic substituent, 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 substitution. I'm tweaking so bad. Substituent, aromatic substituent. But the size of the substituent might prevent the drug fitting the target binding site. A halogen bond involving a chlorosubstituent has been observed for the kinase inhibitor GIF. What in the world are those kinase? Giftinib, giftinib, an iodo substituent has also been observed to form a halogen bond in the anti-cancer drug cobimetinib. Finally, it has proposed that fluorosubstituent in an antiviral agent, glesaprevir, performs a halogen bond. Repulsive interactions. So far, we have concentrated on attractive forces, which increase the strength of the closest the molecules approach each other. Repulsive interactions are also important. Otherwise, there will be nothing to stop molecules trying to merge with each other. If molecules come too close, their molecular orbitals start to overlap, which results in repulsion. Other forms of repulsion are related to the types of groups present in both molecules. For example, two groups of identical charge repel each other. The role of water and hydrophobic interaction. Water. Okay. The role of water and hydrophobic interactions. The role of water is a crucial feature often overlooked when considering the interaction of the drug with its target. The macromolecular targets in the body exist in an aqueous environment, and the drug has to travel through that environment in order to reach its target. Therefore, both the drug and the macromolecule are solvated with water molecules before they meet each other. The water molecules surrounding the drug and the target binding site have to be stripped away before the interactions described can take place. This requires energy, and if the energy required to dissolve it both the drug and the binding site is greater than the stabilization energy gained by the binding interactions, then the drug may be ineffective. ineffective. In certain cases, it has been proved beneficial to remove a polar binding group from a drug in order to lower its energy of dissolution. Dissolution. For example, a polar binding group was removed during the development of antiviral. Huh? For example, a polar binding group was removed during the development of the antiviral drug riton, right, ritonavir. Ritonavir. Okay. Sometimes polar groups are added to a drug to increase its water solubility. If this is the case, it is important that such groups are positioned in such a way that they protrude from the binding site when the drug binds. In other words, that they are solvent accessible or solvent exposed. In this way, the water that solvates the highly polar group does not have to be stripped away, and there is no energy penalty when the drug binds to its target. It is not possible for water to solvate the non-polar or hydrophobic regions of the drug or its target binding site. Instead, the surrounding water molecules form stronger than usual interactions with each other, resulting in an ordered layer of water next to the non-polar surface. This represents a negative entropy due to the increase in order when the hydrophobic region of the drug interacts with hydrophobic region of the binding site. These water molecules are freed and become less ordered. This leads us to an increase in entropy and a gain in binding energy. The interactions involved are small, at 0.1, okay, so basically too small, for each square angstrom of hydrophobic surface. But overall, they can be substantial. Sometimes a hydrophobic region in a drug may not be sufficiently close to hydrophobic region in the binding site, and water may be trapped between those surfaces. The entropy increase is not so substantial in that case, and there is benefit and there is a benefit in designing a better drug that fits more snugly. All right. All right. Pharma pharmacokinetic pharmacokinetic issues in medicine. Pharmacodynamic is the study of how a drug binds to its target binding site and produce a pharmacological effect. However, a drug capable of binding to a particular target is not necessarily going to be useful as a clinical agent or medicine. For that to be the case, the drug not only has to bind to its target, but also has to reach in its first place. For an orally administered drug that involves a long journey with many hazards to be overcome, the drug has to survive stomach the drug has to survive stomach acids, then digestive enzymes in the intestine. Uh, it has to be absorbed from the gut into the blood supply. Then it has to survive the liver where enzymes try to destroy it. Drug metabolism. It has to be distributed distributed dis- it has to be distributed around the body and not get mopped up by fat tissue. It should not be extracted too rapidly, or else frequent doses will be required to maintain activity. On the other hand, it should not be exerted, excreted. Sorry. It should not be excreted too slowly, or its effects could linger on longer than required. The study of how a drug is absorbed, distributed, metabolized, and excreted, known as ADME in pharmaceutical industry, it's called pharmacokinetics. Pharmacokinetics has sometimes been described as what the body does to the drug, as opposed to pharmacodynamics, what the drug does to the body. There are many ways in which medicinal chemists can design a drug to improve its pharmacokinetic properties, but the methods by which a drug is formulated and administered are just as important. Medicines are not just composed of the active pharmaceutical agent. For example, a pill contains a whole range of chemicals which are present to give structure and stability to the pill, and also to aid the delivery and breakdown of the pill at the desired part of gastrointestinal tract. Holy shit. Oh my god, okay. So, key points so we can understand. Drugs act drugs act on a molecular targets located in the cell membrane of cells or within the cells themselves. Drug targets are macromolecules that have a binding site into which the drug fits and bind. Most drugs bind to the target by means of intermolecular bonds. Pharmacodynamics is the study of how drugs interact with the targets and produce a pharmacological effect. Electrostatic or ionic interactions occur between groups of opposite charge. A conventional hydrogen bond occurs between an electron-rich heteroatom and an electron-deficient hydrogen atom. The hydrogen involved in the hydrogen bond is called the hydrogen bond donor. The electronegative atom that interacts with the hydrogen in a hydrogen bond is called the hydrogen bond acceptor. Weak hydrogen bonds can also occur where the hydrogen bond acceptor is a pi system or a hydrogen bond donor is a CH group next to an electron withdrawing groups. Van der Waals interactions take place between nonpolar regions of molecules and are caused by transient dipole-dipole interactions. Ion dipole and dipole interactions are weak form of electrostatic interaction. Pi-pi interactions between two aromatic heteroaromatic rings involve a combination of van der Waals interactions and quadruple interactions. Halogen bonds are similar in nature to hydrogen bonds, but involve a halogen atom rather than a hydrogen. Hydrophobic interactions involve the displacement of outer layers of water molecules which surround hydrophobic region of the molecule. The resulting increase in entropy contributes to the overall binding energy. Polar groups have to be desolated before intermolecular interactions take place. This results in an energy penalty. What is this, football? The pharmacokinetics. Okay. The pharmacokinetics of a drug relate to its absorption, distribution, metabolism, and excretion in the body. Okay. Just gotta have to note those now. Those chapters we just read later. What? Is that it? Oh, wait. Oh, okay. Okay. Yep. I think we'll be live for what, 1 hour? No. Oh god. Holy shit. Honestly. Yeah, so but yeah, that was some bit of studying. Now we know what hydrogen bond acceptors and hydrogen bond donors are, and how what is a drug actually, which is pretty interesting. So now the plan is to get home and note down everything we just read in my iPad and or I can make like a why it's so up. I can make like a big word document with everything, so it's like in one place. That could be pretty cool. Then I can just like Control S and just search what I needed and all that. So that will be one of my plans. And another plan is to edit the video, the YouTube video I did of long line structures. Stay tuned for that. Hopefully you can understand, or like hopefully you can hopefully it will help like getting an introduction to chemistry and its structures and shapes and all that, and how to read them. And yeah, so it's called the series is called what the hell is organic chemistry, and it's gonna be a playlist available in my channel. So those who have a hard time to do chemistry, or just like those who are interested in what chemistry is, can click on that and just learn some stuff, I guess, which is the purpose of this channel, to make people that are afraid of chemistry love chemistry, and to like have a much more clear vision of chemistry. But yeah, it was fun. It's fun to stream again. Like just read a bit, and yeah, hopefully we'll all work out in the end. But for now, zero viewers. I mean, it is what it is. Can't change it. Can't change that, honestly. Yeah. So, well, I'm gonna go get something to eat because I'm starving. And yeah, until next time, I'll see you. And always eat well, stay hydrated.